Continue our discussion on the fundamental theorem of calculus. Specifically, we are going to study FTC2, right? Having already studied FTC1 in the previous video. So for comparison, I've put both the statements together, but let's first focus on the statement of fundamental theorem of calculus 2. Okay, so FTC2 says that suppose f is an integrable function, small f, on the interval AB. Okay, and we define this function capital F, which is in fact the running integral of the function small f, right? So what is capital F? It is the integral from a to x of f of t dt. Okay, the first claim of FTC2 is that this running integral function is in fact guaranteed to be continuous on the interval AB. Okay, that's the easy part. Next, we are saying that if the function small f is continuous, remember we have only assumed integrability so far. If additionally you had continuity at some point x0 in the interval AB, then the running integral is in fact differentiable at x0, and the derivative of capital F is in fact equal to small f at x0, right? So what this tells you, at a higher level, is that it is telling you how to think about the derivative of the integral, right? So you can think of capital F as the running integral of small f, and now you're trying to look at the derivative of capital F. And when does the derivative of the integral coincide with the function you began with? Well, it coincides at points of continuity of your function, right? So at points of continuity of f, the derivative of the running integral of f in fact matches the function value at that point. Okay, that is really the that's the interpretation of the statement of FTC2. If you combine this with the statement of FTC1, essentially FTC1 deals with the integral of the derivative of g. FTC2 deals with the derivative of the integral of f, right? So in one case you're taking the derivative of the integral, in the other case the integral of the derivative, and the hypotheses involved are slightly different, right? So just to maybe say a few words about the relationship between the hypotheses in these two cases, note that in FTC1 and FTC2, in FTC1 you have the function g, okay, and you have g prime, okay, the derivative of g. So this is a derivative, right? And ultimately what it is trying to tell you is the integral of this function, right? On the other hand, in the language of FTC2, well, you have a function f, okay, and then you construct the running integral. We call it capital F, right? And then we were looking at the derivative of this. Right? So this is really, so if anything, between the two statements, the role of g is analogous to the role of capital F, and the role of small f is analogous to the role of g prime, if you will. However, there is a difference between the hypotheses involved for the conclusion to hold, namely that in FTC1, remember, we assume that g prime is integrable. In contrast, in FTC2, we are in fact assuming that f is continuous, right? So the function that plays the role of the derivative in both of these theorems, the hypothesis is different, okay? Specifically, you only need that g prime is integrable in the case of FTC1, whereas for FTC2, I need that f is in fact continuous. And in fact, it is only at points of continuity of f that in fact the derivative of its integral matches its own function value, right? So there is that distinction between the statements of FTC1 and FTC2. So this is just a very high level way of trying to interpret the differences between these two. There is more of a discussion on this in the textbook, which I would encourage you all to refer to. Okay, so having stated and interpreted FTC2 and its connection to FTC1, now what we are going to do is go about the proof of FTC2, where once again recall that the statement of FTC2 is that you have a function f that is integrable on the closed interval AB. First, we need to show that its running integral, capital F, is in fact continuous, right? Then once you prove continuity, you have to show that, the running integral is continuous. And then having shown this, then you have to show that at points of continuity of small f, capital F is differentiable and its derivative is equal to small f at that point. Okay, so that's the statement of the FTC2, which we are going to prove next. So proof of FTC2. Okay, so first the continuity is actually fairly straightforward. So pick some b greater than 0 such that absolute value of f is at most b for all x in AB, right? The integrability of f implies the existence of such a constant b because f is guaranteed to be bounded, right? Now for any xy in the interval AB such that the distance between x and y is at most epsilon by b, let us now look at the difference between f of x and f of y. Remember, we are now trying to prove the continuity of capital F. Okay, so if you look at the distance between capital F of x minus capital F of y, this is in fact equal to the absolute value of the integral from x to y of f of t dt, right? However, note that we can now further upper bound this by the integral of the absolute value from x to y, right, which in turn is less than equal to b times y minus x, which is less than epsilon. Okay, so what we have done is for a given epsilon, we have picked a particular delta, where delta is actually epsilon by b, such that if x and y were within a delta distance of one another, then capital F of x minus capital F of y absolute value is at most epsilon, right? So essentially in words, all we have said is that if small f is bounded, then capital F cannot change by much when its argument changes, right? So that's we are able to bound the change in capital F in terms of the change of its argument, and that in fact implies the continuity. In fact, it implies the uniform continuity of capital F. So F is not just continuous but uniformly continuous on AB. Okay, so that proves the first part of FTC2, namely that the running integral function is in fact continuous. Okay, now so this is part 1 of the proof. Part 2 is that pick some x0 where f is continuous. So suppose that f is continuous at x0 in open interval AB, right? We have to show, recall, that not only is f prime differentiable, but f prime x0, the running integral prime x0, is in fact the original function value at x0. Okay, this is what we need to show. For this, we are going to look at the derivative of capital F at x0. Okay, so the way we are going to do this is to first say that for x not equal to x0, I can write this object capital F of x minus capital F at x0 upon x minus x0. I can write this as follows. Okay, this follows essentially just from the definition of capital F, the running integral function capital F. Okay, so once I have this representation, note that this left hand side is in fact the object whose limit I want to understand as x approaches x naught. Okay, so for this I'm also going to write, so similarly, if I look at f of x naught, I can trivially write this as 1 by x minus x naught times the integral from x naught to x of the constant f of x naught dt. Okay, so using these, let's consider now the difference between the two. Look at the difference of capital F of x minus f of x naught upon x minus f of x naught. This is equal to 1 by x minus x naught times the integral of f of t minus f of x naught dt, running again from x naught to x. Okay, so all we have done is written a representation of this left hand side, right? And note, I want to show that that left hand side tends to 0 as x approaches x naught. That is the goal of this exercise. Okay, and we have written this in terms of 1 by x minus x naught times ft minus fx naught integrated from x naught to x. Now here we have to exploit the fact that f is in fact continuous at x naught, right? So since f is continuous at x naught, so that implies that there exists a delta such that if x and x naught are at most, or yeah, we do it in terms of t then, so long as t and x naught are in fact within a delta distance of one another, that would imply that absolute value of f of t minus f of x naught is in fact at most epsilon. Right? Now you just have to apply this to the previous result, right? So for x and x naught which are less than delta distance apart, it follows that in fact if you look at this difference, f of x minus f of x naught upon x minus x naught minus f of x naught, this thing in absolute value is in fact the integral of f of t minus f of x naught. But f of t minus f of x naught in absolute value is at most epsilon, right? So therefore that integral on x min from x naught to x but divided again by x minus x naught is therefore at most epsilon, right? And so what you have said is that for any epsilon greater than 0, I can give you a delta such that so long as x and x naught are at most delta apart, this left hand side is at most epsilon, which means that this left hand side tends to 0 as x approaches x naught. That completes the argument, right? Because then you have shown that as x approaches f naught, the limit of this object is in fact equal to f of x naught, and that left hand side is in fact exactly the limit is exactly the derivative of the running integral at x naught. Okay, so that's your proof, the proof of FTC2, right? So FTC2, which establishes that so long as you have at points of continuity of small f, the derivative of the integral of small f matches its own function value. Okay, so those are your two fundamental theorems of calculus. What we are going to do to conclude this lecture is to basically prove another result of general importance on the change of variable, right? And this is going to be an application of both FTC1 and FTC2. Okay, so this theorem is on the change of variable. Okay, let u be differentiable on an open interval J. Okay, such that U prime is continuous and let I be an open interval such that U of x lies in I for x in J. Okay, now let f be a function that is continuous on I. Then if you look at the composite function f of u, this guy is continuous on J, right? And the following is true. Integral from a to b f of u of x times u prime x is equal to the integral from u of a to u of b of f of t dt. Right? This is true for a, b in J. So that's the statement of your change of variable rule. It should look familiar to you, where effectively what you would do is basically substitute or apply a change of variable of u of x to say some y, right? In which case the integral of f of u of x into u prime x is in fact interpreted as an integral of f. However, over the interval u of a to u of b. Okay, so this is your familiar change of variable rule. Now let's just get the notation right. The notation here is that you have a function u which is defined on some open interval J, right? Now u in fact maps J to I, right? And yeah, this is not part of the theorem, it's just to keep the notation fresh. And f is basically mapping I to, let's say, R. Okay, so that is how you are talking about the composite function f of u of x over J. Okay, and so the first part is of course to show that this composite function is continuous. That bit is trivial, right? So we have already talked about how continuity is preserved when you take compositions of functions. The main thing is really to prove that second assertion. That is, if you look at integral of the composite function times u prime, that is in fact relatable to the integral of f itself, right? So therefore you can basically do a change of variable where you substitute u of x by some other variable y, right? That's kind of the way we apply the change of variable rule anyway. So now let's go through the proof. As I said, so continuity of the composite function f of u of x is easy. So I'm going to leave that aside and now say fix C in I, okay, and let capital F of u to be defined as follows. It's going to be the integral from C to u of ft dt. Okay, so I'm going to define capital F as some sort of a running integral of small f. Okay, now by FTC2 we know that the derivative of f of u is in fact, capital F of u is in fact equal to small f of u for all u in I. Why is this? Well, because you have to verify that the hypotheses of FTC2 are in fact satisfied, and they are satisfied because of the fact that we have assumed f to be continuous, right? Because f is continuous, the derivative of its running integral will match, well, will match itself. Okay, so therefore we have this. Now let G be basically the composition of capital F with U. Okay, now by chain rule g prime x is equal to, well, f prime of u of x times u prime x, right? But f prime u of x is simply f of u of x times u prime x. Okay, now having written this, you might be able to foresee where we are going next. Essentially what we have done is we have written this object as the derivative of a certain function g, right? And we have used the same notation, so you should therefore be able to see that the statement of the theorem can now be thought of as an application of FTC1. So by FTC1, the integral of, well, f of u of x u prime x, let's say from a to b, is in fact the same as the integral of g prime x from a to b, right? Which by FTC1 is equal to g of b minus g of a, right? But what is g? G is in fact the composition function of capital F with u, right? So it's basically going to be f of sorry, I should write that carefully, f of u of b minus f of u of a, right? Which again, by the definition of f, is in fact the integral from u of a to u of b of f, right? And that completes the proof. Okay, so what I'd like you to note is that this change of variable rule is in fact a trivial consequence, if you will, of FTC1 and FTC2. Right, so what we have done so far is basically proved the two fundamental theorems of calculus, and using these results proved again two very useful operational results in integration, one of them being the change of variable rule and the other being the integration by parts rule.